Hello, brilliant calculus students. We're going to continue Taylor polynomials. So, last time we generalized the Taylor series for cosine x. And so we did that by first creating a tangent line, and then we matched the concavity by taking the next derivative. And if we continued to do that, we would get this sequence. And the factorial pattern of where we took where we had the coefficients of factorials is not unique to a cosine or a sine function. It is every single Taylor series. It'll have something like that because of the derivative pattern of, or the factorial pattern of derivatives. Because if we had something along the lines of x to the fifth, and we wanted to take successive derivatives and find the final coefficient, right? The first derivative would be 5x to the fourth, and then 20x to the third, and then 60x squared, and then 120x, and then 120. And taking 1, 2, 3, 4, 5 derivatives leaves 120, and which is equal to 5 factorial. So when we go down the line of dividing by the successive derivatives, so if we have our function over successive derivatives, so some function to just some derivative power, we're just going to have this factorials, something factorial, whatever derivative we are on. So if we wanted to generalize a Taylor series, we would have to have the factorials. To generalize it, we start with a function, let's say f of x, and we want to essentially create the infinite sum for f of x. It might be something like e to the x, and we don't want to deal with the transcendental number e, and we just want it to be a sum of polynomials so we can compute a lot easier. So we first start with whatever the function is at that value, whatever the c value is. For example, if we wanted it to be centered at x equals 4, we would say c is equal to 4. And then, we didn't do this last time because it was centered at 0, but we're going to have x minus c to whatever derivative we're on. So we are on the first derivative, so we have a 0th power here. And then we divide it by whatever number to whatever factorial we're on. We're going to have we have taken 0 derivatives. We see this f term right here. It has 0 derivatives, so the power of the x minus c is 0, and the factorial is 0. 0 factorial is 1, so we could rewrite this as 1 if we wanted to, just to make this part prettier. And anything to the 0th power is 1. So we continue this. So we do f prime of c times x minus c to the first power over 1 factorial. 1 factorial is also 1, but If you don't want to remember to cancel out some of these things like the 0 factorial and the x minus c to the 0, you can leave these if you just want to remember the pattern. But again, we take the next derivative, f double prime x minus c to the 2. We've taken two derivatives, and it's not f of that, it's f of c, or f double prime of c times x minus c to the second power over 2 factorial. 2 factorial is 2, and then we continue. So f triple prime of c times x minus c to the third power. We have taken 3 derivatives over 3 factorial. And this pattern will continue. So what if we said f of x was sine x? Sine x. We could do this. So let us first write down the successive derivatives. Let's take this to 4. So we're going to say f prime is the derivative of sine is cosine. F double prime, the derivative of cosine is negative sine. The third derivative of sine is negative cosine. And f to the fourth derivative, that's the notation for the fourth derivative, by the way, is back to regular sine, just positive sine. So if we wanted to start expressing this like we did before, let's say we wanted to have it centered at x is equal to 2. X is equal to 2, we can do that. So we're going to say f of 2, which is, let's do this at pi, just to make it easier. Because we know the derivative or we know the function values there. So we could say f of pi, which is sine of pi. Sine of pi is 0. Because sine of pi is 0, this entire term is going to be 0, so I'm just going to write 0, just so we know. And then we have f prime of c, c being 1. I'll write that over here in yellow, just c is equal to 1. I'm sorry, c is equal to pi, just so we don't forget. And then we're going to say f prime of pi, so the derivative of cosine, or the derivative is cosine, so that's cosine of pi, which is negative 1. Negative 1 times x minus c, c being pi, and we literally write x, because we're trying to find a function of x, and so then we divide this by 1 factorial, which is just 1. And then we go to the next term, we say f double prime is sine, and that's just 0, so we just have 0 over here. And then we have f triple prime, which is negative cosine. So negative cosine of pi. Cosine pi, I didn't even finish writing out the x's. Cosine pi is negative 1, and then the negative of that is positive 1. So this is going to be positive 1 times x minus pi. We are on the third derivative here, so x minus pi to the third power over 3 factorial. And then sine 0 again is just 0. So we see this alternating plus minus pattern, just like we did for the cosine. And let's see how accurate our math was with these 4 terms. So here's the 2 graphs overlaid. And you can see that even Desmos, up until about here, is like, they're basically the same graph. Because they're just right on top of each other. And so we said pi, which is about right here. And so it gets accurate with our 4 levels of approximation to about 1 or half of 1 on either side. And if we continue this for several more along the way, this would be a perfect approximation. And so this is how we could use this to estimate values. But let's go do one more. What if we had f of x being e to the x? Let's do e to the 2x, because e to the x is still pretty easy. So let's start with f prime. F prime, we take the derivative of e to the 2x. We have 2e to the 2x. F double prime. Let's only go to 3 this time, so 4e to the 2x. And f triple prime. No, why did I write e? This is supposed to be 2. 4e to the 2x. And this is he to the x. E to the 2x. So we could start writing this out. Let's have it be centered at x is equal to 1. Let's just say c is equal to 1. And now we can start. So we have f of c, which is just e to the 2, e to the 2, plus, let's see, we have prime of c, so that's 2 e to the 2x times x minus 1. And then we just have to substitute in c is equal to 1. This is f prime of c. This is just 2e to the 2 plus 4e to the 2, because c is 1, plus 8. I have to do the x minus 1 squared plus 8e squared times x minus 1 cubed. No, not to the 8th power, cubed. And just look how close we are. We're at x is equal to 1. I'll draw this line here. Like you can start seeing this poking out a bit up here and a bit over here. But it's doing this has a very good approximation for just 3 terms. So if you wanted to estimate values close to 1, you could do this using this series, using this infinite series. So that was Taylor and Maclaurin series. Maclaurin series is just the that c is equal to 0. If someone said, write the Maclaurin series for sine of x, then that would just be do this infinite expansion we did over here for sine x and just set c is equal to 0. That's what the Maclaurin series is. And Taylor series is just the general expansion of this. I hope all of that helped.